Hello everyone and welcome back. So now we're going to the last section in your Excel Everest knockoff. Oh, I know you're sad. You're like, this has been the most fun thing I've ever done in my life. I really hope you're not saying that. You know, I try to make it fun, but it's not that fun. Get out more. So let's go to the last section. It is on normal distributions, which are normal. Okay, so what are these magical normal distributions? Well, normal distributions are this right here, this shape. I'll make myself a little bit smaller. So this shape right here, that's a normal distribution. You might be more familiar with the term bell curve, that thing that you've always been scared about because you've heard that in college some teachers grade on the bell curve, even though you're not quite certain what that means. And what a bell curve is, it means that a teacher wants a certain number of their grade, a certain percentage to be C's, B's, A's, D's, and F's. And so, depending on what your grade is, you might make a 99, and if everybody else in the class made 100, you get an F, because that's how you have to kind of average it out. That's a really weird way to grade. I don't grade that way, and I've never actually met a teacher who did. I think it's an urban legend. Maybe like there was one teacher who did it. Never seen it though. Okay, so this is the bell curve. It's all about the probability that something is going to happen. The further we are away from the center, the less likely it is going to happen. For example, if I change the mean, that's where the center is. We can see that's going to move over. Ooh, fun, moved over. If I move it back though, I'll go ahead and move it back. If I change the standard deviation, which you have no idea what that means yet, we're going to see that it gets very wide and broad. If I increase it insanely, it gets even broader. So the more I change the standard deviation, the broader it gets. And just so you know, this is more or less a flat line. It's just been scaled so it doesn't look like a flat line anymore. Because these are all 0.02. I didn't actually have enough decimal places here to show it all. Okay, so this right here is just showing the probability. The more deviation in my data, the more likely it is that values far away from the average might be seen. The less deviation in my data, the more likely they are to be close to the center. In fact, if I make this 0, it throws an error. Okay, 0.0000. Make it a really small number. And you can't actually see it because it just instantly happens and then stops. That was too little. Let's try again. 0.1. Okay, so that works. I can do this one right here too. And you see that I'm getting further and further in every single time. And 0.025. Bring it in even further. And let's try again, 0.001. Ah, too little. I can't make it. There's not enough resolution right here to see it all. Okay, but this is getting shorter and smaller and smaller and smaller until eventually it's just a straight line where all the values happen right here. This is important. Now, why is this important though? You're like, I'm going to take his word for it. Don't take my word for it. Let's look at something. Okay, so let's say because I'm an engineer, I have my son help me with projects, which I do. He's hilarious. He's 3 years old and he has a little orange hammer. He helps me hammer things. It's great. I love it so much. Okay. So with my son helping, I measured the length of a board 20 times. And without him helping, I measured it 20 times. So here's my measurements, here's his measurements. Now, he's trying to help me, but usually when he helps me, it's not that helpful. So if I just look at the max, min, and the mean, or the average number right here, we can see there's quite a bit of variation. For example, the max value we got when I measured with my son was nearly 10 inches, and the lowest was 6.5. When I measured it 20 times, the worst I did ever was 8.25, and the least was 7.75, which averages out to 8 inches, which is what it should have been. And with my son, averaged out to 8.33. Okay, so it didn't really help me all that much. But, while this is averaging out to the right data, answer right here at least, how can I put a number on that deviation? Like, which of these we're doing better? We're going to learn about that soon. But what I want to show you is that if I look at my 20 values right here for both my son and myself, you see this shape. Now, this isn't probably going to jump out at you instantly as a bell curve. However, if I had measured 1,000 times instead of just 20, right here. This is measured 1,000 times without help. You see that bell curve beginning to happen. Where this is just simply how many times do you see a number between 7.8 and 7.85 right here. So if I look through my 1,000 values, this is how many there are. And you see now I've got a bell curve. So most of the values are found here at the center, while I find less and less values further off, with almost no values out here. There might be some, but it's just so small I don't see it. So this is helpful. What this tells us is that in real life, error follows a normal distribution. If you're measuring something, the values you're going to measure are going to be following a normal distribution. Most of the time, they'll be close to the center, close to your average. However, depending on how precise you are, precise is how close together all your measurements are, will depend on how much spread there is in your data. Maybe there's that one time where your hand slipped and you measured way far off. Maybe there's that one time where you weren't paying attention and you were just too far away. Or maybe it's just your device itself is not accurate enough. My wife and I were trying to take our son's temperature when he got sick a while ago before COVID-19. And that thermometer, it changed by a few degrees every single time. Not very precise and not very helpful. My son's temperature was maybe 104 or 97. I really don't know. He survived. So this normal distribution is good for errors. It helps us see what's going on. We can actually quantify this normal distribution and quantify this error and understand how we can get certainty about things, how we can make sure our designs don't fail by using this. But we'll learn about that next time. So I'll see all of you later. Bye-bye.